Welcome to the next video in the Systems Programming video series. In this video, we are proceeding into section 13.4 of the textbook, Dive into Systems. We'll be talking about inter-process communication. And since this is a somewhat long section, I'll probably split this into 2 or 3 different videos to get through this section. Now, the first section is about signals, and signals are basically a way for one process to communicate with another process by means of a very constrained collection of possible commands. So I'm going to run somewhat quickly through this because really only the most high-level description is needed for our purposes. So here's a nice collection of examples of signals. And so sig segmentation is a signal that one process can send to another, which gets triggered, for instance, when dereferencing a null pointer. Okay, fine. You can interrupt a process, which that happens when you type Control-C on a keyboard in a terminal window, and this causes the process to shut down, terminate, whatever, and so on, right? So there are these specific signals, right? There's a finite list of them. So this is a pretty constrained way to send information from one process to another. So they aren't all just bare signals. So there's the alarm, and you can tell it to do the alarm every 2 seconds. There is this p-kill. And I believe this number here is the process ID that you are killing. This is like the name of the program. I'm not totally sure why you need to specify both of them. Oh, I guess it would make sense that you need to specify both of them because you could have a single program run in many instances. So yes, I think that makes sense. In any case, though, the point is just that these signals can have arguments to them, like here. So they're not just written as these bare commands like that all the time, but in any case, I'm not sure that I want to talk too much more about that, but I guess it is worth just briefly reviewing that they're going to give you here an example program, and you can run this program and then issue these signals in the terminal. And it will demonstrate the use of signals, right? It'll send the signals around, and you can see the behavior of sending a signal. And so you can see here how a C program has signal, or can have signal handlers. So a signal handler could, for instance, handle the alarm, and the signal comes in as an int. And so you can print the signal number to see exactly what signal came in. You can flush the standard out. That's probably just for printing purposes. And you can issue another alarm, right? So this sends another signal, right? So basically your signal handler can itself send signals. So it receives and sends signals. Then you can have this cont, which, what do we guess? This is a continuation, one would expect. And so that basically it just lets the alarm keep going. I would think that's what that does. There's the interrupt. And then we can see in the main function how these signal handlers are getting used. They get used with this signal function that takes the identification of the signal together with the handler. And notice, this is something that I don't think we've seen this at all through this video series, but it's worth pointing out that you define the function here, and then the function itself gets passed in as data to another function, making this a high order function, because it is a function that receives a function as an argument. So that's when you first encounter that, it's a bit head spinning. At least it was for me, but it's worth getting used to because it comes up a bit, especially when you get into functional programming design and stuff like that. But anyway, so let's move on. So the sigchild handler, sending a sigchild signal is how a parent process can be alerted that a child of the parent has terminated. And that can be nice because, alternative, like what you need things to happen in a certain order. And the main way that we've discussed that up to now is to use the wait command. But what if you don't want to necessarily wait? You'd like your process to continue running, but you would like to also be listening for when the child process terminates. So, right, if you're waiting, then you're kind of doing anything until you hear back from the child process, and that might slow your program down in ways that you don't want it to do, or entirely halt your program in a way that you don't want it to do. And so what you can do, right, like sort of the compromise here between completely halting until the child has terminated versus running with no sense of what the child has terminated or not, and not knowing at any given moment of the run of the program what has gone on, is to have the program always listening for a sick child signal. And so we can see an example down here where we are writing the handler, like what happens when the parent process receives the sick child signal. And, what does it do? I guess it sends it into this while loop for whatever reason. I'm going kind of fast here. But so in the main function, we invoke the sick child handler that we just wrote. But down below, we are free to run whatever is the rest of the program that we wanted to run. But okay, that's enough of signals. The other way, well, not the other way, one other way that processes can communicate to each other is to do message passing. There are primarily two ways of doing message passing. There's pipes, which is just one-way message flow, right, or information flow, and there's sockets, which is two-way information flow. So if you've ever used pipe in the terminal, then in fact this pipe is a way for the terminal to pipe information or establish, to create an information pipe from one process. In this case, that would be from the cat process here over to the grep process over here. So that establishes a pipe, right? Data is flowing from here to there. And so that's your pipe. A socket is two-way, and it's more common in networks where maybe you have two computers talking to each other, both sending, both receiving information. So one would do that over a so-called socket. And finally, there is this shared memory, and this is going to be important for us. This is really the tool that we're going to use for the remainder of assignment number 9. And so this is what we need to understand. Effectively, the idea here is that you may have two different processes. So this is process 1, this is process 2. We're not going to worry about what a page is, but just they've got some of their own memory. You would imagine this, I think, is more like virtual memory, but we're going to skip talking about those concepts. And so they can both refer to the same RAM, so this would be shared memory. Well, if you have shared memory, then in a sense, the two processes can communicate with each other through their shared ability to see the same memory, right? One process can write to this memory, the other process can read what the first one wrote, vice versa, so on. The command shmget is how you can create shared memory. I believe to do that you need to, it requires like a key, and I think if I understand these things correctly, this 100 would be like key for the shared memory. So you tell it what the key is, which I think in some sense indicates, this memory occurs in RAM. You then need to tell it how much memory is allocated for this shared memory. And possibly, I think there's a third argument, but I think it's almost always null anyway, so we don't need to worry about it. But in any case, the point is that we sometimes need multiple processes to be able to operate on the same memory. And the C command to do that is this shmget, or at least that's one way to do it. I think there's actually somewhat more, there's another way that is more preferred, but shmget is in some sense the more from scratch way of doing this. And so we want to start learning that before we learn the better, but also harder to explain, I guess, or other way of doing it. So the thread is the abstraction of an execution control flow. A process has a single thread of execution control flow. So effectively, for every process, there is a thread. Every thread belongs to some process. There's like one-to-one correspondence. What's the difference between a process and a thread? Well, the process refers to like all of the virtual address space and everything that goes with context of the entire process. The thread is the execution control flow. So it is narrowly the sequence of steps that the process is executing. Threads share execution state by reading and writing to shared locations in common address space. If a global variable is affected, all of them can see the same effects. And I guess that's about it. Then there's this summary, which usually the summary doesn't contain much that I feel I need to talk about but haven't already talked about. So yeah, I think actually, yes, I was going to do this in multiple videos, but I guess that's actually it.